Welcome. To understand the future of AI, we must first re-examine our definition of depth. For the last decade, deep learning has been dominated by a specific architectural metaphor. We visualize intelligence as a skyscraper. We start with data at the bottom, and we stack layer upon layer upon layer, each step adding complexity, processing features sequentially. This is depth in layers. But the paper we are exploring today, Nested Learning, challenges this fundamental view. It asks, what if depth isn't about going asterisk up asterisk, but about going asterisk in asterisk? Imagine instead a learning process defined by context, where inside one optimization problem, there exists another, and inside that, yet another. Here, the model doesn't just filter data, it refines its own learning rules within narrowing contexts. This brings us to the core thesis of our discussion. The illusion of deep learning is that architecture the stack is the only path to complexity. Nested learning argues that true intelligence emerges from asterisk depth in optimization asterisk. Let's peel back these layers and see how this illusion works mathematically. Building on the introduction, let's dive into the first major contribution of the paper, expressive optimizers. To understand this, we need to revisit something you've likely seen 1,000 times. Consider the standard parameter update equation used in gradient descent. We take our current parameters, theta, and adjust them by the gradient of the loss, scaled by a learning rate. In modern optimizers like Atom or SGD with momentum, we don't just use the raw gradient. We store a history moving averages of gradients or their squares in what we usually think of as a state buffer or a storage bin. We view this as a static memory, but the authors challenge this view. They ask us to look closer at this buffer. What if I told you that this storage bin is actually an illusion? Mathematically, maintaining these moving averages is equivalent to a shallow, linear neural network. This optimizer isn't just storing values, it is an associative memory module. It takes the stream of raw gradients as input and learns to compress this context into a single update vector. So, standard optimizers are effectively simple, shallow learning models training alongside your main network. This realization is powerful. If an optimizer is just a shallow network, what happens if we replace it with a deep one? That is the question we will explore next. Building on the limitations of fixed architectures, nested learning proposes a fundamental structural shift. Instead of a single model updated by a rigid equation like SGD, imagine splitting the system into two distinct levels. At the top, we have our main model, the network actually performing the task, but beneath it lies the deep optimizer. In this paradigm, we replace the simple update rule with a fully expressive neural network, often a recurrent neural network, acting as a nested learner. Here is how they interact. The main model sends its performance feedback, the gradients, down to the optimizer. The deep optimizer processes this information and sends back specific parameter updates. Crucially, because the optimizer is a neural network with memory, it doesn't just react to the current moment. It observes the history of gradients, learning the trajectory of the loss landscape. This enables what we call higher-order in-context learning. The optimizer isn't just calculating, it is learning how to learn, adjusting its strategy on the fly based on the context of the training process itself. Building on the limitations of external optimizers we just discussed, the paper introduces a second major contribution, self-modifying modules. In this paradigm, we move the optimization logic inside the model architecture. Instead of a static network waiting for an external teacher, we have a meta-learner embedded alongside the model's parameters, or weights, represented here by theta. Watch what happens when data arrives. The input isn't just processed for an output, it flows into the meta-learner. This internal module analyzes the data and computes its own update rule. It generates a specific adjustment, delta theta, instantly modifying the model's weights. The model effectively rewrites itself on the fly, learning the update algorithm based on the context of the data. This is the essence of nested learning. The architecture itself learns how to learn. Building on the self-modifying capabilities we just explored, we must ask, how do these models actually store their experience? The traditional view, and indeed, How we often model LSTM or transformer memory relies on a binary separation. We have short-term memory for the immediate context and long-term storage for the distant past. It is discrete and often rigid, but the nested learning framework proposes the continuum memory system. Instead of buckets, imagine memory as a continuous spectrum, a decay function of time. Here, there are no hard boundaries. Information simply fades smoothly as it moves into the past. Crucially, this decay doesn't mean loss of access. The system allows for retrieval at any point along this timeline. Whether a memory is fresh or distant, if it is relevant to the current context, the model can reach back and activate it. Mathematically, this is formulated not as a discrete sum, but as an integral over history. The model aggregates past states weighted by a kernel function, allowing it to fluidly blend the immediate past with long-term dependencies. Now that we've engineered the components, it's time to assemble the final architecture, the Hope module. We start with our self-modifying core, the engine capable of learning its own updates. To this, we attach the continuum memory, our infinite library of past experiences. These aren't isolated, they are tightly coupled. Let's see how they handle a task. A new task arrives. The core begins its optimization process, but as it modifies itself to solve the problem, it generates valuable context. Instead of discarding this context, the core offloads it to the continuum memory. This is the storage phase, preserving the learning state. Simultaneously, the memory system searches its vast history. It retrieves relevant past contexts and feeds them back into the core. Empowered by both immediate adaptation and long-term memory, the core produces a robust prediction. This isn't a one-time event. It is a continuous, lifelong loop. As tasks change, the system constantly adapts, stores, and retrieves. By nesting this optimization loop within a memory system, we achieve the holy grail: continual learning without catastrophic forgetting.